t and h such that t plus 1 plus h, t up to tn plus h, it holds that this distribution, this is the joint distribution, is same as the point where as some points where x is taken, the value of x is taken at point t plus 1 plus h, t1 plus h. This h generally we call it a lag. Okay, we call it lag. So after lag, if I find that these two distributions are same, then we call the is stationary. So that is the so-called finite dimensional distributions of the process are invariant under the shift, under time shift. Actually, we shift the time from t1 to t1 plus h. If the h is constant, so there is a shift, only a shift of the time. From t1 to t1 plus h, t2 to t2 plus h, like this. So there is a shift in the time points. So if the distribution, joint distributions of these two sets of variables are same, then we call it a stationary. So this is the definitions of strict stationary. So here this equal D means indicate the equality in distribution. These two distributions are equal, same. Now, this is the strong stationary concept of strong stationarity and the weak stationarity. This is the concept of strong stationarity. Now, in the first panel, we have the same pattern of distributions over time. The pattern are same, the distribution pattern are same over time. But this is hardly realized in the reality. Hardly we find this in reality. So in reality, what we find that the distributions are different for different time points. So where the mean and variance of the distribution changes. Here the mean and variance are same, but here the mean and variance are changing. So in that case, so I cannot say if the distributions is like this, then I cannot say it is a stationary series in terms of strict stationarity. So I cannot say this. So, but if this is like this, I can say this is stationary series. Now, in this, Now, in this panel, you see this is a distributions. This is a joint distributions of a particular y. And now these joint distributions here it is the time, and this is distributions of y. So if we take all distributions for all the time point, then the mean is same and the dispersions also the same, or the variance are the same. So here we can say that this is a stationary series. But here in this second or third or fourth, in any case, it does not satisfy any figure. This figure say 2 does not satisfy the conditions of stationarity, since there is a change in the variance of the series. Here in panel 3, there is a change in the variance, or there is a change in the mean values of the series. So these are all non-stationary series. Now, these are the non-stationary series, since it does not satisfy conditions of strict stationarity. Now, if we have two variables, two points, we get the result n is equal to 2, then we get xt1 and xt2 is the same that of xt plus 1, t1 plus k and t2 plus k. Actually, these distributions I have already said, in one axis I measures the time and another axis I measures the value of the variable. So the distributions, so here you see in these distributions, this is the distribution. This distribution is same for all the year, all the time points. So if it is t and it is t plus 1 or t1 and this is t2, then these two distributions is same. Now, if we write t1 plus k is equal to t2, we get the same distributions xt2 and xt2 plus k. Thus, it just depends on the difference k, t2 minus tk, which is called the lag. The k means lag. Now, this covariance is the autocovariance functions at lag k. This is covariance functions. It's called autocovariance. Why it is called autocovariance? Because I take the same variables. That is why auto. But there is a difference in the time point. So this is called the autocovariance. Now this autocovariance value at lag k. So I take gamma k. This is the lag k is called the autocovariance functions. Now, if k is equal to 0, then it is simply the variance. This covariance is simply the variance because the two are the same. Both is xt and xt, so this is the variance. But autocovariance where this t is different, the first one is t and another one is t plus k. Now, the correlation is, as you know, the correlation is the covariance divided by standard error of x into standard error of y. So, in this case, actually variance of so in the autocovariance coefficient depends on the unit of measurement xt. It is convenient to consider autocorrelations. Those are free from unit of measurement. So it is called the autocorrelation functions. This is called the autocorrelation function. As I told you that the first one is the numerator is the correlations of two correlations of two variables at two different point of time with lag k. This is the lag k. So this is called the autocorrelation function. Now there is, as we find that these strict stationarity conditions is very complicated, and for that purpose we are generally use the weak stationary concept, weak stationary conditions, or it is called the uh, autocovariance conditions. Now, this is here, uh, here you see that the mean is constant. Expectations of xt is equal to mu t, which is constant. So this should be constant, variance should be constant, and this is the covariance term. This is gamma t t2. There are two time points t t2, and this when t is equal to t1 is equal to t2, the autocovariance is just variance as in my earlier case. So long stationary process need not have to have a finite mean or variance. This terminology implies that weak stationary can be more stringent condition than strong stationary. For a covariance stationary series, we can define the autocorrelations between these as gamma s by gamma 0. I think I have already told you these things. Gamma s by gamma 0 is the autocorrelations between the two time points. One t and another is t minus s. So these are the properties: constant mean, constant variance, has a theoretical covariance between the value of yt, and that depends only on the difference apart in time, Covariance yt minus tau is expected value of this. This depends only on tau. Tau is the difference between two time points, that is tau, or we call it lag. So it depends only on lag. Now, there is a advantage of the stationarity, because the property I can call. So because this memory, short memory, if it is a stationary process, then there is it has a short memory. I will come to that. Before that, what could be the testing of the stationarity? How can I say that this series is stationary or not? So there is some preliminary process or some some primary testing of the data, like check plot of the data, consider plot of the time series. Shocks have temporarily affect the series only, that the series will revert to its time, invariant mean and finite variance. Consider the autocorrelation functions of data which should decay rapidly for a stationary series. If the data content trend, the series may be stationary around the trend. Formal unit truth test. So these are some informal tests, and formally I have some unit truth test. One most common thing is common test is that autocorrelation is to consider the autocorrelation function. Just a minute. Now,
जो पूरा भारतवर्ष 16 राज्यों में विभक्त था, काशी पोषण
it is a non-stationary process or non-stationary series. We call it a random walk model. Now, suppose the stochastic trend model is like this: delta yt is equal to A0 plus Et, in which A0 is equal to 0. Then you cannot predict the future value of yt, since it depends on the change depends only on a stochastic term epsilon t. Suppose, for example, price of a stock from one day to the next day is completely random. As such, the current price should be equal to yesterday's price plus a white noise term. Now, this white noise, you cannot predict either whether it will go up or go down. So, since it is a pure stochastic term, if you actually, this is actually yt is equal to yt minus 1 plus epsilon t, A0. Now this is the yt is equal to yt plus epsilon t. This is the equation. So if you just a minute, to take the solutions, the general solutions, the first order difference, this first order difference equation represented by the random walk is this. Yt is equal to y0 plus sum of epsilon t. Now these are the mean. These are the mean. Mean is constant in t, but it is constant. This if we go to like this and take the expectations, then these expectations of ui, all ui will be 0. Expectations of all ui is 0. Only the expected value of y0 will be there, which is a constant, I know. So expected value of yt is a constant. So this is constant. In the random walk model, the expected value maybe of yt is constant, but the variance is not constant. The variance is time dependent. So as time increases, variance will also increase. So this is a non-stationary model.